I had a discussion with few people at Stony Brook, and the recurrent theme was that it's quite an amazing meeting where kind of at the same session, you first hear about phenomenology of finite temperature QCD, then some exotic string amplitudes, and then integrability in EDS-CFT. Well, we had a very nice illustration to this morning when we started with like things like BF theory and twistor strings, and then heard about pressure being measured in pascals, which is, well, I don't recall when I last saw this. And I really think this is a feature rather than a bug of this collaboration. And so that gives me, I'm the last speaker, so there will be no further changes. So I decided, motivated by this, to update the title of my talk, which will be From the Worldsheet Axion to Eternal Inflation. And actually, well, people know that I like many colors, so that also gives me opportunity to add even more colors to the emblem for our collaboration. And so the plan, okay. So the plan of my talk will be, well, I will start with a brief summary of Worldsheet Axion, and we already heard at Stony Brook Andreas' summary, which is kind of from experimental viewpoint, from point of view of lattice measurements. So mine will be more like from the theorist perspective. And then I'll explain how one can sneak eternal inflation into the what is mostly lattice QCD talk. And this is based on a work to appear with Guzman Hernandez Scheffler. And then I'll conclude with another couple of comments about Worldsheet Axion. So first of all, well, I should kind of, I always say it, for many of these developments, their lattice for us is the main source of data. And in this context, when we say lattice, we really mean mostly the work of Andreas and Mike Tepper. So I won't be very accurate with my references during the talk. So I apologize in advance to people whom I missed. But for sure, I want to give credit to these guys for providing these measurements. And the kind of measurements we're talking about is the measurements of the spectrum of long closed flux tubes. By long, I mean that these are flux tube around compact direction. This is the slide which I also shown many times. So for many years now already, the experimental summary of these measurements, and the theoretical analysis can be put on one slide, which says that in D equal 4 Young Mills, one finds, but there are many string levels, and you'll see some of them later in the talk. But in terms of meta content of the Worldsheet theory, one finds two Goldstone bosons and the pseudoscalar Worldsheet axion, and there is a mass and coupling constant, the coupling constant, they're extracted from the data. I'll tell more about this later on. And at D equal 3, the field content is essentially just a Goldstone, and there is no indication for any other pronounced resonance, massive mode. And maybe I spent too much time thinking about this stuff. So initially, it was a bit of surprise to find this pseudoscalar axion, and I think many people had expectations there should be some kind of radially symmetric Bayesian mode. But a posteriori, to me, right now it looks almost obvious from perturbative QCD viewpoint, because we kind of know what are the degrees of freedom we expect to find inside the flux tube. These are at high energies they should be partons, and we're in pure glue theory, so partons means gluons. And kind of if one think in the in the continuum language or in terms of lattice operators, so the way you produce a flux tube, you have a long long Wilson line, this p-ordered exponent, and the elementary excitations which are there at our disposal, these are field strengths of the gluon. And so if you if the string goes along the direction, so if you attach the plaquette, which kind of oriented in the same plane, that has quantum numbers of Goldstone boson. Well, and it's naturally that's a local displacement of the flux tube, and that's we find both in 3D and 4D. And in 4D, the other option which we have is to introduce the field strengths perpendicular to the flux tube, and that's exactly matches the quantum numbers of the axion. So Mr. Schiffman, who is not here, he was complaining at Stony Brook that we called it axion. I think it's fair, we should call it gluon, but there are too many gluons, so one should use some different name. And to some extent, like again, maybe that's an artifact of looking at this for too long time. At this point, I kind of reached the stage where I would be surprised if there was something else, because it would be just hard to interpret in terms of partons. So, well, given that, so the zeros of the question list, which I might have. So, first of all, well, is it really true that there are no other Worldsheet modes? So you shouldn't take my word for granted or like any feelings for granted. So we want to check that. And well, if so, kind of is there any structural insight left to be learned from this axion? So kind of one can say, okay, we understand degrees of freedom, it's strongly coupled theory, and kind of we have intuition for what degrees of freedom are, and then they do whatever they do. So it's nice to measure their properties, but kind of what is there really something qualitatively new insight which we can learn from these measurements? So I think for me, as a theorist, spending most of my time on this, that's the key question. Well, and of course, there is another set of questions which also would be fun. So can we observe axion not just in lattice data, but in real-world experiments, such that like exotic hadron spectroscopy, maybe hadronization dynamics, or whatever else you might think about. And I should say, well, my talk today will be mostly focused on these first two questions here, and I'll mention something at the end about the last one. But to start with, let me give you a very brief summary of how we extract information of physics from lattice data. And well, first of all, as everybody knows, lattice provides Euclidean data. In this context, these are finite volume energies of the strings. And well, relating these to real-time physics, or kind of to things like, by that I mean here really just by something like an action or and parameters of this action, is notoriously hard. It's a kind of classic hard problem in lattice QCD, and I actually feel like that it's not kind of appreciated enough beyond the lattice QCD community, and we're trying to make progress on that also. Well, in this case, the ground state energy, well, is very well measured, and actually for ground state energy, one can also calculate it very nicely. We already saw this plot before. So here, well, this is the data for different gauge theories versus the theoretical curve. And this theoretical curve is the sum of universal term in the low energy expansion, where the only assumption in this expansion, in this universality, is that there are no additional massless degrees of freedom on the Worldsheet of a string, apart from the translational Goldstone modes. And it's kind of very nice to see such a beautiful agreement between theory and the data, but at the same time, it's telling us that it's really hard to extract anything from this data. So kind of using particle physics analogy, there is a huge standard model background here. If our goal is to explore kind of UV of the theory, non-universal properties, then this observable just not very useful. So one wants to look at the excited states, which would be analogous of building particle accelerators. in particle physics. And kind of the way to go for excited states is to relate Euclidean energies to scattering data through kind of what is similar, what's called in lattice community Lusher formulas. So it's basically a relation between scattering amplitudes and Euclidean energies. Well, one complication which we have here that this is harder than in kind of typical lattice setup because Worldsheet theory is gapless. So that means, for instance, winding corrections coming from loops wound around the circle, they're not exponentially suppressed, they're only power law suppressed, and one need to take care of those. And on the other hand, it helps that the Worldsheet theory lives in 2 dimensions, and moreover, again, as a consequence of this universality, so it's leading IR asymptotics, it's integrable. And that allows us kind of to use many tricks, technical tricks to play, which is like things like asymptotic beta ansatz, but it's really more or less the same as the Lusher formulas in high dimensions. But there is then also thermodynamic beta ansatz, which is the way to account for winding corrections in the context of for integrable models. Well, it would be very nice to kind of push this systematically further, but I think it's fair to say that at the moment, really, it's kind of some combination of tricks, and there are real challenges to push them further. But let me give you kind of the short summary of the state of the art, how it's being done. And it's also, it's kind of the shortest way to phrase it. It's using, again, a trick, which is goes under the name of TT bar deformation. Namely, the logic is the following. So we start parameterizing our theory. That's what's the S matrix of our theory, which stands on the left-hand side here, in terms of what I will call undress theory and a certain phase factor. And kind of interesting fact about 2-dimensional models that there is this kind of deformation at the level of S matrix correspond also to meaningful deformation from the point of view of the Worldsheet theory. And then the remarkable fact, which was found in these papers by Smirnov and Malochikov and Tatev and collaborators, that when you have 2 theories connected whose S matrix is connected by this formula, there is exact relation between finite volume spectrum of these 2 theories. Namely, if I denote the energy of the kind of deformed theory by like consider any energy of the deformed theory and kind of label it by parameter L squared, which is parameter which appears in this deformation, then as a function of this deformation, like level by level, each of these energies, they satisfy this simple PDE. And all you need to do, you need to kind of, if you know the spectrum of undress theory, then you need to plug it as initial data and evolve this PDE to the physical value of the parameter, and that gives you the spectrum of the deformed theory. And here P is total momentum of the total KK momentum of the state. So the way we use this trick is that, yes.
Okay, it works now. I missed, maybe you said, why do you want to TT bar deform?
Well, I'll explain momentarily. So far,
okay, so you didn't explain.
Yeah, I didn't explain it yet. But so far, it's just kind of exact fact. There is this curious fact. There is this exact relation between 2 spectra, and kind of coming to this question. So kind of the procedure which we're using now can be phrased as the following way. So basically, we calculate spectrum in the undressed theory as good as we can. And in practice, kind of at least in the data which I will be showing here, there are attempts to go beyond that. But in practice, we restrict to 2 particle states and apply EBA formulas there, so without winding corrections, but just Lusher-like formulas. And then one evolve the result to the physical value of L squared, where by physical I mean using the, well, because this L squared, basically it's inverse, set by inverse tension of a string as measured from the ground state energy. And kind of answering your question, so the motivation for this procedure is the following. So the observation is if you start with a theory of just, if there are only Goldstone modes, which I described by Nambu-Gote action, and you ask yourself, what is the Andres theory? Then the Andres series of Nambu-Gote action for Goldstone modes of a string, it has like infinite series of interactions of the form dx to the 4, dx to the 6, etc. So Andres theory, it removes all these leading order derivative interactions. And so this TT bar dressing exactly accounts for all kind of scattering and also winding corrections associated with those interactions. So we're left with only high-dimensional operators. Moreover, kind of these operators, the leading set of high-dimensional operators, it's also universal. It's, well, they're proportional. All operators at this order, they're proportional to d minus 26. So there's something interesting about those operators. They know that this is a theory which lives not in the non-critical string theory. And then there are, of course, higher order non-universal term. So kind of you may think about this procedure is some kind of its analog, so at least I think about it as kind of analog of RG improvement. So picking L is like picking the normalization scale when we're doing dimensional regularization, say. So it's kind of in principle, it's up to us. We can calculate in any of this family of theories. They're all exactly related. But we want to choose the one where kind of naive perturbation theory has the best convergence, and based on the fact that kind of removing this dressing factor removes all leading derivative interactions, that provides a hope for better convergence as we go from low energies to high energies. So does it answer the question? Okay, so applying this logic to lowest two particle states, that actually produces this plot. So let me just say let's plot using all the data. So if you see here, so the dashed line, so the solid line there in the middle, that would be just taking kind of leading order Goldstone interactions. They're free Goldstones dressed by this procedure. And three colors here, they refer, so these are two particle states describing collision of two Goldstones. And we have a long string in 4 dimensions. So there are O2 symmetry characterizing them. So there is a scalar, pseudoscalar, and spin 2 mode. So if you restrict it to leading order dressing, then we would get this solid line in the middle. If we included universal one loop effects proportional to d minus 26 and dress them, then one would get these two dotted lines here. And there are only 2 lines because at this order, so the blue line is a scalar. The blue line would be degenerate with the red one. So at this order, that's a prediction. And clearly, that's not how data looks like. So this procedure results in reasonable agreement for the states, but the red points, which is a pseudoscalar, they're completely off. And so that what one does, one introduces essentially resonance in that sector, and kind of you can fit its mass because this line is nearly horizontal, which tells that the mass gap corresponding to the state is roughly independent of the length of the string. So you can determine the mass almost by eye. And this coupling constant is determined instead from the exchange of this pseudo-scalar mode in the T channel, which contributes to splitting between scalar and spin 2, and that's the result one gets. So this was obtained with Victor and Raphael Flauger a long time ago by applying this procedure. Well, the procedure was phrased a little bit differently at that time, but it's essentially equivalent to what I just said, and to the old data by Mike and Andreas. So in the next few slides, I will show kind of what I will try to do. I will try to test this kind of meta content which I presented for you, and to see whether there are any surprises with the most recent data. And it's kind of both this data and analysis was published in the paper with Andreas, Mike, and Tsonghalu, who is also here. And so in particular, this is kind of the updated version of the same plot. These are the same three states, but well, there are no surprises here, no big changes. But now, kind of pausing for a sec, one may ask that, well, extended this, now we don't have a theory of just massless goldstones. So my logic, which I used to answer your question, doesn't apply, strictly speaking. It's not clear why this dressing procedure would improve convergence, because we have massless goldstones, but we also have a massive axion. So a priori, there is no reason to expect that this dressing will be useful for states involved in the axions. Well, on the other hand, directly calculating the finite energies with the states is very challenging, because in the Goldstone language, if I think about this axion as a kind of resonance which appear in the scattering of two goldstones, now we'll be talking about states like with 4 goldstones or even more. So that's really hard by using conventional Lusher methods. If we want to proceed, well, we had to be somewhat optimistic. And the reason, the source of optimism was provided by a suggestive piece of numerology, which was observed in our paper with Victor some time ago. Namely, the observation is that so first of all, if one takes a theory of 2 free goldstones and a massless axion and just dresses it, so the observation that that integrable model is compatible with 4D Poincare symmetry. And furthermore, another observation is that, and for some reason, I don't see everything which was on my slide, but it's OK. So also the leading coupling of that integrable model of this pseudoscalar particle to 2 goldstones shown here, it's numerically within the numerical error bars here, it's the same as measured on the lattice. So somehow that suggests that also axion goldstones interactions may be well described by the same dressing procedure. And so basically, based on this indication, because we didn't have other choice, we have data, we want to try to analyze it. So we decided to proceed essentially starting with approximation that we have axions, which are like the theory we have goldstones with phase shift given by dressing plus terms which universal ones and extracted from exchange of the axion. And we have an axion which doesn't interact directly with the goldstone. So that's our undressed theory. And then we dress it. So in that sense, kind of there will be no, well, I introduced this in doing fits for initial states. I introduced new parameters, which is the mass and the coupling constant. But there will be no new parameters introduced when we go to other states involving axion, which as we'll comparing what one gets by applying this dressing procedure to the states. And kind of again, there are 2 questions. First, are there states which look completely off? Are there indications for any other massive resonances? And is kind of how well also quantitatively we can understand those states. So, well, let's start looking at some of the states. So first of all, this is now the kind of different symmetry channels. This is the pseudoscalar channel. So the red one is the axion which I was describing before. And now there are two additional excited states. And actually, one shouldn't be impressed too much by this dark red curve. So when I told you that I kind of don't introduce new parameters, I cheated a little bit, because kind of this state is really described just scattering. So kind of what one sees here is a classic like avoided level crossing picture. And so this state is mostly composed of the massive axion. But this state, this red one, describes scattering of 2 goldstones in the pseudoscalar channel. So really what we do, we just use that state to extract the phase shift is a function of energy using Lucier formula. So there is not much predictive power here, but kind of one gets, if one replots it on the phase shift, one gets kind of phase shift which roughly looks the same, which is kind of nice resonance phase shift. So that's what one gets. Well, on the other hand, these blue states, so here it's more interesting. So in terms of kind of quantum numbers and in terms of kind of our logic, this state would correspond to two phonons in a scalar channel plus additional axion. And so here, really, these two curves which are shown here, the dashed curve, that's what one would get if one just treat these two phonons. Well, we know their phase shift already from the previous measurement. And if one just adds non-interacting axion to those states, and instead the dashed line, if one applies dressing procedure to, as I described before. And so here there is really no new parameter introduced. And well, we see that it kind of matches. Well, there are some deviations, but one should keep in mind that these shorter strings are really very short. So they're really very close to the confinement phase transition. There will be always deviation there. But for large range of lengths, we get a reasonable agreement here. So let's keep going. So this is perhaps even more interesting state. So this is excited states in 0++ channel. So the leading state, the ground state here, again, these are two exciting phonon. And these states, they roughly correspond, the mass gap is nearly constant. It corresponds to roughly twice axion mass. That's what one expects. One expects to find the state with two axions. And the dashed line would be, if we model these two axions as just free, non-interacting, and the solid line, again, which we get by applying this procedure without just closing our eyes, putting on the computer no new parameters. And well, it's actually rather surprising. This is completely non-universal. But it looks like the two-axion interaction is actually, and we'll see later why it may be surprising for many other reasons, but it looks quite well captured by this dressing procedure. So let me give you another example. Well, that's Axion-Goldstone scattering. So what the state here, it's now the state with states which I was discussed so far. They had 0 KK momentum. Actually, there are analogous states which are kind of boosted. And that's a nice cross-check that we see Axion also not at rest, but moving. And we do see. So it's all consistent there. I'm not showing to you those states. But here, the state with momentum 1. And this state corresponds to kind of the quantum numbers. Well, the ground state here is just a single Goldstone boson traveling around the circle. So it's very well approximated essentially by free massless particle up to some small winding corrections. But the next state in this channel, that corresponds to axion at rest colliding with this phonon. And again, the dashed line here, that would be the state if we just take axion and phonon non-interacting. And the solid red line is what one gets by applying this dressing procedure with no new parameters added. And again, it looks like this procedure really captures well the interactions between axion and Goldstones. So, well, kind of to summarize, there are more plots like this which I can show. Well, I showed you, admittedly, the best ones, the most spectacular. But for sure, we don't see any new anomalous states. So the old states which we see, they can be explained in terms of this matter content. So definitely, on the other hand, definitely these free dressing ansatz cannot be 100% correct. So we know that that's not the full answer, in particular because what it doesn't capture. So if you think about it, so kind of you think about theory on the Worldsheet, kind of there is induced metric determined by Goldstones, and there is a mass term for the axion, and there is square root of minus h phi squared interaction. So there is this kind of interaction between phi squared and two Goldstones. And if you write this in like-cone coordinate, this dx squared is the same as d plus x, d minus x. So what it tells us that in the scattering of Axion and Goldstone boson, there is reflection. There is a possibility for, if you have colliding Axion and colliding Goldstone, there is a probability for, due to this vortex, for reflection. And this TT bar ansatz doesn't allow for that. The S matrix is just multiplies the leading answer, so it doesn't introduce any new reflections. So for sure we know that there are deviations from these ansatz, but these deviations are kind of proportional to the Axion mass. So to the extent you may think about this Axion as a light particle, they expect it to be small. Well, and actually indeed, so this is the corresponding state. So this is again Axion and photon state, but to now we look at not the Axion at rest, but the Axion where this doesn't happen, but Axion colliding with the photon that now both of them carry a unit of kk momentum, and we have two states related by parity, and in the absence of reflections, these two states would be degenerate, and on the other hand, reflections they lead to splittings between these states. So here again, the dashed line is the approximation if we treated Axion non-interacting with Goldstone bosons. So the solid red line, that's what one gets in this dressing approximation, and that would be prediction for two states. Well, instead, kind of this two set of dark and red points, that's the lattice data. So, well, we see clearly that the splittings are there, which is good. We expected to see them. But also, well, we see that indeed it's kind of compared to the shift which we get from just non-interacting theory. So especially if one goes to high energies, then it kind of seems to capture the leading order interactions. So kind of my personal conclusion from this, well, apart from the fact that, again, it looks like we don't see any indication for additional massive particles. Also, somehow this ansatz, this dressing ansatz, works sufficiently well to kind of warrant a closer discussion of the physics of these dress series. So is it kind of why does it happen that they capture this Worldsheet dynamics, well, I think quite well. And also that, as promised, that will give me an excuse to sneak in some eternal inflation into this lattice QCD talk. So let me tell you a bit more about this series. So far I described them for you at the level of like S matrix or deformation of the energy spectrum. But there is also action formulation for this series. And in terms of action formulation, there are two kind of almost equivalent formalisms. These are series of 2D gravity. And kind of it's what might be called flat space GT gravity. And really, kind of, essentially, the second order formalism, one introduces metric, and one introduces, well, there is a kind of cosmological constant light term, and then one introduces Lagrange multiplier, which forces the curvature of metric to be 0. So it's a very, very simple theory of gravity. And at the classical level and on the plane, this formulation is equivalent. There is equivalent way to reformulate it, which is basically use first order formalism. So here there is this dyad E. So the metric is not independent variable. Metric is the square of this dyad. And this axis, there are some remnants of some Lagrange multipliers, which one uses to use first order formalism. And really, I will be using kind of that formalism is better suited and for many purposes, things like calculating finite volume spectrum. But this second order formalism, it provides kind of useful intuition for some of what I will be talking about. But in particular, in this context, kind of one immediate advantage of this first order formalism, well, that we manifestly see that we're talking about some kind of string theory, right? Because we have these x variables, which one may think, well, and there is Lorentz symmetry acting on this axis. So one should think about this axis as some 2D target space coordinates of this theory. And then there are additional degrees of freedom kind of on the Worldsheet represented by this matter Lagrangian. So that's kind of the way to think about this series. And using this formalism, one can reconstruct many properties. Like first, so as I said, it's manifestly look like a theory of a string. One can reproduce the dressed S matrix, and kind of the way it works. So it's a very simple theory of gravity. All what is left from gravity, curvature is said to be equal to 0. But all what is left from gravity is that kind of clocks and rods in gravity, they are dynamical. They're presented by dynamical quantities. And so one should kind of, to get the dressed S matrix, one should reformulate scattering as observed by somebody who only measures target space, as we always do when we talk about particle, point particle, relativistic particles, so we talk about strings. And there is exact relation. So this action provides relation between axes in the vacuum, they just proportional to Worldsheet coordinates, but in the presence of excitation of the Worldsheet, there is this relations between excitations of axes and stress tensor. And using this relation, one can essentially rewrite the kind of usual decomposition for arbitrary like scattering field in the creation annihilation operators as a kind of in a asymptotic region. One can rewrite them as a decomposition kind of Fourier modes controlled by axes, and that gets the scattering expression for the S matrix. Also, one can calculate finite volume energy evolution just really by doing this theory of gravity. Turns out to be sufficiently simple that one can really brute force calculate the exact torus partition function, where by torus I mean that I take target space to be a torus. One can just brute force calculate it, and from the answer reproduce this evolution equation, which I wrote for you. Well, and even there was a nice paper by Offer. So one can, in principle, calculate off-shell correlators for this theory, kind of which uses this axis as a kind of anchors of kind of relational observables. And I think, well, it's fair to say that not much physics what yet is extracted from these correlators, and I was going to say kind of goes in this direction, although I won't be using directly the answers. But kind of not surprisingly, these correlators, they look similar to just usual kind of expressions for scattering amplitudes in string theory, which we use in kind of vortex operators constructed of this axis. Okay, so this is the theory, and kind of as follows from the definition of this theory, kind of there are two natural phases to think about. Namely, I have this parameter lambda I. Didn't tell you, probably it's written somewhere. Yeah, it's written here, that this vacuum energy which appears here, it's related to the deformation parameter which I had in my S matrix formulation. Namely, it's kind of inversely proportional with the minus sign. So which tells us that, well, this theory kind of has two phases, and sometimes kind of, at least I usually call one of them is a kind of good sign phase, another bad sign phase. And the reason is that for kind of negative cosmological constant phase, well, that kind of corresponds to positive tension string. That corresponds to dress scattering amplitudes which produce time delays. So that the exponent is such that you get time delays as a result of scattering. And it gives, for sufficiently large circle, it gives a finite volume spectrum. And then there is a critical value of the circle size where the ground state acquires imaginary energy. And it looks exotic at first sight, but actually it's a very welcome feature if one thinks about this in string language. That corresponds to kind of the fact that string Worldsheet theory, it ceases to exist when circle is smaller than some size. It's kind of in critical string, it's usually phrased as a consequence of winding tachyon condensation in construct of gauge theory. It's just spontaneous center symmetry break. You know, if you think about this as a thermal circle, that's a hagedron transition. So actually, that's not a bug, that's a feature. If one wants to apply this for kind of Worldsheet theory. So that's a good sign. Well, and then there is another sign where cosmological, and sorry, there is yeah, I messed up the sign here. It's a positive cosmological constant. So lambda is taken to be positive. So that corresponds to negative tension string. in the scattering, one gets advances rather time delays. And for any compactification size, the finite volume spectrum looks quite strange. There is some finite number of states with real energies, and then sufficiently excited states, they all have imaginary energies. And it's easier to understand what's causing those. Namely, if you have a theory with time advances, and you're trying to compactify it in a circle, if there's sufficiently large excitation in between, time advance can be larger than the circle size. And so by making a compactification, you produce a closed time-like curve. So kind of the interpretation, at least my interpretation for this was that this kind of theories, they're bad, but they're not so bad in finite volume, but they really don't allow to be consistently put in the finite circles that creates closed time-like curves. Okay, this is the summary. But there was a kind of question which was bugging me for a long time. And this question in puzzle is the following. So what if I consider a theory like this? What if I consider a theory where I have a negative energy vacuum and a positive energy vacuum, which can be metastable, but I can make it arbitrarily long-lived. So from the point of view of full S-matrix description, well, this is a good sign theory. The S-matrix has only time advances and should have a healthy finite volume spectrum, a sufficiently large circle. But on the other hand, we know when it is in context of field theory, we can probe the physics of a metastable vacuum, for instance, by setting up a large experiment in the ground state, creating a large bubble with a metastable phase, and somehow, if it all works through in the standard way, in this context, there will be time advances, which kind of don't look like they show up anywhere in the S-matrix. Also, kind of on also the finite volume, one would get strange things. So this is a puzzle which I should say kind of we didn't fully resolve it, but it's really kind of what I'm trying to understand here. And let's first discuss a less confusing case. Namely, let's consider the situation where both vacua are good sign, both vacua have negative sign. At first sight, it's already a little bit puzzling because in the dictionary which I showed for you, this vacuum, it corresponds to a tension string with larger tension, positive, like there is a flip sign between tension of a string and energies of this vacuum. And this vacuum naively corresponds to a string with a larger tension, and this corresponds to a string with a smaller tension. And so it looks like the decay which we have here, it would describe decay of a string of smaller tension to decay of a string with larger tension, which is not what one expects. Well, unexpected to this, naively it looks like I was telling you that Hagedron appears as a property of the ground state of the theory, but here the Hagedron radius of the metastable vacuum would be larger, so it would appear before the Hagedron radius corresponding to the true ground state. So something is off already here, and well, actually what I just told you is just both the statements are wrong, and one should really be careful, and to understand what happens, we should look, so what happens in the, if one starts the physics, studies the physics around metastable vacuum, then in the action which I had before, I had these two parameters equal to each other. Well, I dropped here the last term, which is dx, which is total derivative, which doesn't affect any infinite volume physics and just provides some trivial shift for finite volume energies. But these two terms, they're now different because changing the vacuum energy, it affects this term, which is kind of the square root of minus g in the first order formalism. So it's now determined by my metastable vacuum, but this term stays the same. Well, of course, it's easy to kind of bring things back. One needs to do a while rescaling of the dyad. But after doing this while rescaling, so first of all, one reads kind of the physical tension corresponding to the metastable vacuum, and one gets this expression. So I recall that this lambda plus is the vacuum energy here. So, well, actually, we see that because of this rescaling, the metastable vacuum actually does correspond to string with a larger tension. So this kind of intuition works. But there is other consequence of this rescaling. So all mass scales in my theory, which I had, they will get rescaled by the same factor, the same Weil factor, similarly how this tension got rescaled. Well, but this is just really rescaling of parameters. No, I don't think there is Also, it is in it is in flat space. So then the path integral is localized on the flat matrix. So yeah, it's really the constant scaling symmetry here. I call it while, but okay. So well, that leads to the following consequences. So it's interesting now to think what happens when lambda plus approaches 0, right? When we start entering this dangerous territory. So first of all, because of this rescaling of all massive fields in this metastable vacuum, they become physically infinitely massive. So they kind of become very massive. You're left with massless modes, if they're present any. The deformation parameter goes to 0. So the result of the scattering goes to 0. However, bubble nucleation rate, if one kind of looks at the standard semi-classical result for bubble nucleation, the action stays the same. That's straightforward to check that the bounce action stays the same. But just because of this rescaling, the nucleation rate diverges. So basically, because the bubble nucleation rate is some prefactor, dimensional full prefactor times to e2 minus s. The s is the action of the bubble, of the bounce. And this dimensional prefactor has dimension of mass squared. So because of this while rescaling, it gets very, very large. So it's kind of quite exotic situation when you have what looks like a healthy low-energy effective field theory, but this effective field theory becomes kind of infinitely fast decaying due to there is some rapid UV-dominated instability associated with the physics which gets decoupled to high energies. So that really suggests that this kind of lambda plus positive vacuum corresponds to qualitatively new physics. So let's try to understand. So kind of to probe this physics a little bit. And there are two ways one may think of relating the physics of this stable and metastable vacuum. One is I've also already mentioned. One can think about starting from stable vacuum and creating a large bubble of metastable one. And another is a common de Luce bubble describing decay of the lambda plus vacuum. And basically, we can look at both of these configurations and using this dictionary between unrest Worldsheet coordinates and rest coordinates, try to understand what these configurations correspond to geometrically. And the crucial feature is that there are kind of, in these relations, there are some signs between x and sigma. So it may be that there will be sign flips between Worldsheet coordinates and target space coordinates. So in particular, if you think about how nucleated bubble nucleation looks like, nucleated bubble looks like, well, that will be the picture. So this lambda plus, that corresponds to metastable vacuum, but this is the region of far out here. It corresponds to a region of negative tension. So then there is this sign flip in the middle. So it's really from target space point of view, it looks like a fold like that. And inside the fold, there is a true vacuum with a positive energy, positive tension string. And then, kind of as usual, this bubble starts expanding. But what expansion means from the point of view of this bubble, usually, kind of before deformation, it was corresponding to true vacuum eating the false vacuum. But here, just the size of the fold grows. But because, kind of roughly speaking, this is a negative tension string, so it wants to expand. So the whole region gets larger, but it doesn't correspond to transition from metastable vacuum to the true ground state. Instead, and it's intuitive. So that's kind of instability of negative tension string. So it won't create these kind of wiggles. So you create a wiggle like that, which grows. Well, and that's kind of my justification to, because that looks a lot like what kind of people call eternal inflation, when you have a naively metastable vacuum, but the tunneling process doesn't result in the complete decay of the vacuum state, but instead of in a mixture kind of new vacuum and old vacuum. Yes? No, but there is no, because you see, it's negative tension, but it's 2D string, right? There are no Goldstone modes, so there are no. Yeah, but those have. No, because perturbatively, we know what it is. Because perturbatively, that was the theory which I wrote. It was a meta theory with metastable, stable metastable minimum, and coupled to these dynamical coordinates. So there is no perturbative instability in that vacuum. So kind of the rules of the game here is that one reads dynamics and the dress theory from these dynamical coordinates, and that's how it looks. It's a peculiarity, of course, of two-dimensional strings that you may have negative tension without introducing ghost modes, but that's what happens here. And kind of I wanted to try to draw a different process where instead kind of more robust in some sense, where you start with something, you start from the ground state, and you're trying to create a bubble of metastable phase. So I'm still finding a good way to draw it. But basically, what happens there, it's crucial for this process that direction inside the bubble, direction between physical time and Worldsheet time get mismatched. So instead of like scattering process, what it looks like, it's you have a long string, and then there is a kind of some baby universe being created somewhere. It expands for a while, then it contracts and rejoins the string itself. And analogy of that, if you think about path integral of a relativistic point particle, one does include, in this path integral, it includes also trajectories like this. And this is the reason why when we talk about relativistic particles, we're using field theory, because that's been interpreted as a result. Actually, path integral for point particles doesn't produce for us usual transition amplitudes. It produces the answer for Feynman propagator, right? And we interpret this process as the fact that there is a pair of particle-antiparticle was created, and this one annihilated with this, and this keeps propagating. That's how causality is restored in the full theory. But here it's more interesting, because instead of point particles, we have extended objects. So really, there is some dynamics going on in these objects. And I find that this situation is very interesting. So it looks like what looked in the initial theory, the kind of what looked like S matrix. In the deformed theory, it really corresponds to some kind of different observables. It would describe some, inside there would be this creation of like baby universes annihilation. So it's fun to think about, so this theory of gravity looks, and I myself thought that it's too simple to have interest in part of gravitational dynamics, but actually there was always this superficial analogy with this bad phase, which is positive energy phase. It's a little bit like de Sitter, and the bad phase is negative energy. It's a little bit like anti-de Sitter, but I thought that this analogy is too superficial to be interesting. But I think there are some of the interesting issues which one may ask in this context, which looks like a solved theory of quantum gravity. But now coming back to QCD strings, I think, well, first, one lesson we learned, that definitely this dressing theory is quite unusual. But on the other hand, well, it's this dynamics, it can be formulated in terms of string-like dynamics. So it is a series of very, very peculiar strings. But another lesson which we learned that kind of it's to properly understand this dynamics, it's very important to think about these fold configurations here. And actually, even kind of considering, instead of thinking about these exotic situations, although I would say they're not that exotic, because kind of we know that inflation can be done without metastable vacuum, and we just think about potential which grows and has positive energy. So really, this bad and good phase in this theory, they're not that well separated as one may want to think. But let's just consider the simplest setup, which is we have a good phase, subluminal, and we have a heavy particle in this phase. And if one uses this dx equal to t equations to reconstruct how the corresponding string configuration will look like, starting from kind of finite size particle, some kind of soliton, and taking thin wall limit, then one finds that the particle will look like that. So actually, it will look like fold configuration like that, and the size of this fold, it looks like well, it's proportional to the mass of the particle. So that's kind of already tells us this is very different. So one way to get massive particles on the Worldsheet in the QCD context is to add heavy adjoint degrees of freedom, like heavy quark. That should correspond to massive degree on the freedom on the Worldsheet. But we expect that the answer will be quite different, right? Because adjoint quark just corresponds to to Dirichlet boundary condition. It doesn't create a fold like that. In other words, when you scatter excitation of the heavy quark, you don't expect that the time delay will be proportional to the mass of the quark. You expect it to be proportional to the energy of incoming quanta, just geometrically, because it makes string longer, but not proportional to the mass of the quark. So clearly, that leads to expectation, which would be very interesting to check using data, which Andreas is trying to obtain now, that these ansatz which we're using for calculating finite volume energies, it should start breaking badly when one adds heavy adjoint quarks on a Worldsheet. And so one should think about so this matter, which is added in this dress description, it's different kind of matter. But on the other hand, for gluons, for excitations corresponding to gluons, maybe that's not that bad, because they gluonic degrees of freedom, they really correspond to some geometrical degrees of the degrees of the freedom of a string. So that's maybe part of the reason why this kind of description works reasonably well for Axion. But anyway, definitely it does look that this dressing reproduces well the data which we have. So in this theory has some features which we want to have, but it's that provides a hint of how to extend it to get more realistic setup. Okay, so that was my excursion to internal inflation story, but really it was motivated by the fact that this theory, it keeps reappearing when we think about Worldsheet's theory of a string, and I think it's important to understand why it captures many aspects of Worldsheet dynamics, but also what it is missing. But coming back to the Worldsheet, let me point out there is another puzzling property, namely, well, I heard with Andreas that also they see the same axionic mode also with open strings, and this is this orange points here, and the mass gap roughly corresponds to the mass of the axion. And this actually, that was known for a while. There was old papers by Julius Kuti from 2004 where already these kind of states were seen, and we were very happy to see that for open strings one sees the same degree of freedom with the same mass gap. Of course, the data which Andreas has now is much more spectacular, and it will be fun to properly analyze it with TBA-like techniques, which we're doing now, also thinking about doing this now. But the observation which we did recently, realization which we had with a bunch of people, including Sharzad Zari, who is a PhD student applying this here and sitting in this room, that actually this fact is puzzling. And this puzzling for the following viewpoint. So, well, the shift symmetry of axion is broken by the mass, but the mass can be thought as a small shift symmetry breaking, but it's also broken by this operator. And like earlier density, this operator, there is no way to make a topological invariant, like quantity out of this operator in the presence of the boundary, because that's a self-intersection number of a string. So this operator seems, in the presence of the boundary, it seems really to break shift symmetry of the axion. However, to have this fact that for this mass gap to be given by the axion mass, that's strong indication. Again, one should do proper analysis, but it's pretty clear it corresponds to Neumann boundary condition at the endpoints, which is puzzling given that the shift symmetry is broken. And moreover, the main point of this paper was to look at the look for signs of the axion-like excitations for actual meson spectra. And I should say real-world data is much more messy than lattice data. But there is an interesting candidate which actually works surprisingly well numerologically. There is some exotic hadron which is tempting to interpret as having additional axion. But again, that would only work if also for rotating strings, the boundary condition at the endpoints for Neumann, which is even more confusing because for rotating strings, the endpoint is really singularity from the effective viewpoint. So given shift symmetry is broken, that looks very surprising. So this is my last slide to conclude. Well, I just say that I think one of the most surprising lessons of the last few decades after DSCFT was discovered, that gauge theory dynamics is actually very closely related to gravitational dynamics. And confining strings, they provide very kind of basic reason for that, because in the large n limit, we are left to study the Worldsheet theory, which is theory of a 2D gravity. And of course, this is theory of non-integrable theory of 2D gravity. This is what makes understanding of confining strings is so hard, so challenging, but also potentially very rewarding, and I hope we'll make further progress. Thank you.